This is going to be chapter 1, kind of review stuff for Chem 1211. This is stuff that you may remember from physical science or from high school chemistry, and not something that we really cover in class, but that we do want to review a little bit if you need it. You may not even need this video, but if you do need it, um, you can watch, and if you have any questions, definitely let me know. So chemistry is the study of matter, and particularly we're going to start with atoms in this textbook. So what is an atom? It's the smallest particle of an element that cannot be divided into smaller particles and remain what it is. So if you have an atom of gold, that's the smallest piece that you can have of gold, and it still retains the properties of gold. An atom of carbon is the smallest piece of carbon that still has the properties of carbon. What is an element? An element is a pure substance that can't be separated into simpler things. So if I have a sample of gold here, every atom is gold. I can't separate it into atoms of gold and atoms of something else because there isn't something else. It's all atoms of gold. Repeating, like copy pasted, same atom. Sometimes elements exist as just a bunch of atoms put together, and sometimes elements exist as molecules. Like this is an example of two oxygens put together, and we would write it as O2. Now, this is still an element, oxygen, but it's just a molecule. I think they probably meant this one to be blue to show the example here. Um, but this one is an element of nitrogen, but two nitrogens put together, we would say N2 because nitrogen exists as a molecule. So this would be nitrogen, and this one would be oxygen. I think they probably meant for all of it to be blue just to show examples, and all of this is gold, AU. Compounds are two or more elements bonded together. So this would be nitrogen and this would be oxygen. So this molecule, or this would be a sample of NO, nitrogen monoxide. Here we have, I don't know the color symbol for purple and green here, but we essentially have like a 1-to-1 ratio of each of these. And so because there is this ratio that stays the same, we can think about it as this repeating pattern over and over again. We're gonna copy and then paste, 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 paste. That makes it a pure substance. There's just one thing there, nitrogen monoxide. There's just one thing in here, whatever green and purple is in the code for the coloring. So this is called the law of definite proportions, meaning that if we have a compound, it's the same proportion of its elements every time, even if we change the state of matter. So water is H2O, whether or not it's a solid, a liquid, or a gas. So that's what makes it a pure substance. A compound has the same proportions. If we make it H2O2, it's no longer water, it's hydrogen peroxide. And if you know anything about hydrogen peroxide, that's very different than water. So we classify matter by first deciding, can it be separated? So is it pure or not? If it can't be separated by a physical process, meaning non-chemical reaction, like just physical thing like melting, boiling, picking it apart, with tweezers or something, right? Like if it can't be separated, like with something that's relatively easy, not a chemical reaction, then we call it a pure substance. I like to think about pure substances as having one ingredient. And then if it has one ingredient, we have two options. Can it be decomposed by a chemical reaction? So is it two or more different elements? Then it would be a compound. We could break it down into, like, for example, water. We could break it down into hydrogen and oxygen with a chemical reaction. We can't do that with like just melting it, right? But we can do that with a chemical reaction. So an element is all atoms are the same. A compound is all molecules. I guess I'll leave it at molecules and we'll talk about different terms later, but all molecules are the same. So they all have the same ratio of atoms. We've talked about that already. And then now we have mixtures. So you can separate it by a physical process. For example, if I have salt water, I could boil the water off and I could separate the salt and the water. Then I have a mixture. Or if I have a pepperoni pizza and I don't like pepperoni, I can take off the pepperoni. That's a physical process that I did to separate that. That's a mixture. If it's uniform throughout, meaning that it's the same, the top part of it, the bottom part of it is the same, we call it homogeneous or homogeneous. And think about something like vinegar, black coffee. If you grab a Gatorade at the gas station, that's same at the top as it is in the bottom. You don't have anything floating around. Versus if you have a salad dressing like this Italian dressing, we've got an oil layer, a vinegar layer, and it's just a bunch of spices and things in here. You probably have to shake it before you use it. That's something that's heterogeneous, meaning that it's different at the top and at the bottom. So this would be like salad dressing, that pizza I was talking about, Chex Mix, those things are heterogeneous. It's hard to differentiate between compound and a homogeneous mixture. So ask yourself, if you look at the ingredients list, would it be one ingredient? If it's one ingredient, compound. If it's two ingredients, homogeneous mixture, two or more ingredients. So vinegar, for example, is acetic acid and water, not a compound. It's homogeneous mixture. And you might not know that just by looking at it, right? But if you actually looked at the ingredients list, you'd see that it's more than one thing. You'll do more of the scientific method stuff in lab, and we don't really need to go into like you're not going to be tested on what's the part of scientific method. But the scientific method is not maybe what you have once learned it to be as like a step, and we always go step by step, and we have a beginning and we have an end. The scientific method is cyclical and it doesn't always follow the same steps. So let's say that we start with the traditional first step, which is you see something interesting and you maybe you have a guess, propose a tentative explanation. Oh, I see this cool thing. I wonder if it's happening because of this. And so you're like, well, I guess I could test that, couldn't I? And then you test it, and then you look at the results. You either accept the hypothesis, you reject the hypothesis, and you go back to step one. You modify your hypothesis and be like, well, it's not entirely wrong, but something else is going on here, so we need to test it again. Or you see results, but something went wrong with your experiment, maybe, and you have to redo your experiment. If you get to the end where you actually have a model or a theory where you're like, hey, I thought this was the reason why I saw this thing. Actually, I tested that guess, that hypothesis. I'm going to establish that I think that this is the reason. That's now a theory because it's tested. Then what I have to do is keep testing it over and over again. I got to publish it. Other people are going to test it. And then it will become a theory that can be adopted and maybe taught in a textbook one day or something, right? When we say in common language, like just colloquial language, a theory, we actually probably mean hypothesis. So, for example, you're like, oh, I watched the last episode of Stranger Things. Here's my theory about what's happening. Um, that's not a theory. Like, you haven't gone through this whole process. What you observe something, you have a guess, you have a prediction. That's a hypothesis. So if you're ever around somebody who's like a scientist and you say like, "Oh, that's my theory," they may be like, "Oh, I don't use that word." There's not just a theory. A theory is not just a thought, just an answer, just a guess. A theory is actually a hypothesis that has been tested over and over, rejected, modified, refined, to then be tested again and again and again before you even get to call it a theory or a model. Um, the law of multiple proportions is that you can have um, two different masses of an element react with a given mass of another element. So we can have like carbon, for example, and oxygen react together. Carbon and oxygen can come together in a 1-to-1 ratio, or it can come together in a 1-to-2 ratio. But basically, the law of multiple proportions means that the first element, um, these ratios have to be a small whole number ratio. Don't worry too much about this. You're not going to be tested on what's the law of multiple proportions. We never actually really cover it, but you may have seen that before. Again, it's not something that is covered, so don't worry too much about that. So again, pure substances, elements, or compounds. Properties of pure substances are intensive or extensive. Intensive, don't matter, it doesn't matter how much you have. Extensive, it matters how much you have. Physical properties are ones that you can measure without changing it. So like I can measure the temperature of water. I can measure the melting point of water. What temperature does it melt? I'm not changing it from water to something else. I'm just changing it from water to a different form of water. And so, I don't have to do a chemical reaction to observe a physical property. Chemical properties can only be observed by chemical reaction. So if I want to know, hey, is this thing flammable? I can't just observe that. I have to test it. And if I light it on fire and if it's flammable, well, that's a chemical reaction now that I did. And it's not the substance it used to be. Like if I want to know if this paper is flammable, if I light the paper on fire, it's not paper anymore. It's smoke and soot, and I can't really use it as paper anymore, right? So that's a chemical property. Density is an intensive physical property. So we can test the density of this gold nugget, for example, without changing it. We just need to know its mass and its volume. Both of these things are physical properties we can measure, and it doesn't matter how much you have for the density. This ratio will stay the same. So if you increase the mass, you increase the volume, and the density would go up the same amount. So density is an intensive property. This is called volume displacement. So, if we think about volume, typically you might think like length times width times height. But if I can't measure length times width times height of something irregular like this gold nugget, then what I can do is I can measure the milliliters, which is another type of volume of some water in a graduated cylinder or something, and then plop in my nugget and measure the new milliliters and just take the difference. Call this volume displacement. You can measure the volume of your own body if you were to take a bathtub and put markings on it, like a graduated cylinder or a beaker, and then you could measure the amount of water that was in the bathtub before you got in, totally submerge yourself, have someone measure the volume of water after you're in the bathtub, and that would be the volume of your body, right? So this takes up space, it's going to displace the water, and the difference would be the volume of the object. If you do lab, if you're taking lab, which I hope you're taking the lab class because it is very helpful to take both at the same time, you will do this method in the lab. We're going to be using a framework for solving problems in this class called COAST, and we're not going to do each letter out every time, but it is helpful for you to know just how we're going to be thinking about solving problems. First, we're going to collect and organize information. So instead of just looking at a word problem and then immediately going straight to your calculator, we're going to write down what do we know, what formulas do we need to use? What definitions? What does that thing mean in the problem? Then we're going to analyze it. So we're going to see if we can figure out what connections we need to make. Are there steps that we need to use to solve the problem? Are there different conversion factors? We're going to do conversion factors in this class that we're going to use. And then we can perform the calculations. And then we want to think about our answer at the end. So does our answer make sense? Do the units match up? And this is going to be a really good way to check our work. If the last part doesn't really make sense, maybe you need to look back at a previous step and decide where something went wrong. So here's a question if you want to just look through and see which properties you think are chemical or physical. I would pause it and just go through and think chemical or physical for each of these properties. So hopefully if you haven't yet, pause the video and do that. If you have, pause the video. Your answers are going to be in the next slide. So if you said that A was chemical, B was physical, C was physical, and D is chemical, that's correct. So gold medal can be made soluble by reacting it. That's a chemical change. Melting, even though it changes state of matter, it's still gold. Solid gold and liquid gold, same thing. So melting is physical. Hammered into a sheet, it's still gold. It's just now it's in a sheet. That's physical. And then treating the ore with a solution reacts with, that is describing chemical reactions. Hopefully you got those right. If not, let me know if you have any questions. And there's more explanation here if you want to go back into the slides and read through all of that. Now for mixtures, again, homogeneous mixture, same throughout, heterogeneous, different. So if you can see chunks of things floating around, it's probably heterogeneous. We can separate mixtures by evaporation. So water evaporates, and then it's left behind salt. If you have like salt water. Here it is showing filtration. So if we have some particles that are solid and there are some smaller particles that go through this. There's like a filter under here. You can't see it, but there's like a filter paper under here. It's kind of like separating your pasta from your pasta water, right? It's based on size. So filtration separates based on size. Distillation separates based on boiling point. Filtration separates based on size of particle, and chromatography based separates things based off of something called polarity, which we'll talk about later. And so this is an example showing that we have a mixture, it'll separate out. So a mixture of different inks can separate out into multiple colors. So go ahead and take a minute to answer this question. Do you think it's an element, compound, homogeneous, or heterogeneous mixture? And pause and work on this one. All right, so hopefully you've paused the video and you've worked it out first. Answers are fruit salad is a mixture. That's it's not mixed uniformly, therefore it would be heterogeneous. Filtered air is hopefully homogeneous. And so if I'm breathing clean air, it is a mixture. It's not pure oxygen. It is a mixture of different things, but it shouldn't have chunks of things that are different, right? It should be kind of the same all throughout. Helium is an element. It's on the periodic table, and that's a good hint there. And then solid carbon dioxide or dry ice is a compound because it's multiple elements together in a chemically bonded together. Explanations and some tips here for how to distinguish. And then you have a summary of all the pieces of the problem here. States of matter, solid, liquid, gas. Solid has definite shape and volume. You can't really, it's hard to change the shape and the volume of a solid. Liquid has definite volume, but it takes the shape of its container. If you have water and you pour it into a cup, it's going to take the shape of that cup. A gas has neither definite volume or nor definite shape, so it can spread out as far as it can, take up that much space, and also it will take the shape of whatever container that it's in. And then throughout the textbook, they're going to be using these different colors for different elements. So this would be a good screenshot to just kind of have in your notes. Common ones we're going to use are carbon, nitrogen, oxygen, and hydrogen. So if you have to think about the colors of any of them, I would say these four are going to be the ones we use the most. Phase changes. So you probably learned this in some sort of science class before you got here. Just serves as a review. Let's do the easy ones first. So liquid to gas is evaporation or vaporization. Gas to liquid is condensation. Solid to liquid is melting. Liquid to solid is freezing. And then the hard ones, solid to gas is called sublimation. This is what dry ice does. And then gas to solid is called deposition. This is like if you have something really, really, really cold, the water vapor will immediately turn to solid. So let's see if you can look at these images and tell what's the change of state for the forward direction and what would the change of state be for the reverse direction. So see if you could kind of look at the diagrams and tell what these would be. So pause it and try it. All right, so your answers for this one. So let me just go to the summary. So for A to B, we go from close together, but not really ordered. So let's call this a liquid. And this one is very orderly, so we'll call this a solid. Liquid to solid would be what? Freezing, right? So freezing would be this direction. If we switch it to the other direction, solid to liquid would be melting. We have this one, it's a solid, and then we're turning it to gas, which is very open. So this would be solid to gas. This is what dry ice does. This is called sublimation. So the reverse would be gas to solid deposition. Make sure that you could look at images like this. These would be easy questions on a test, right? Like just to make sure you know, like, oh, this really ordered pattern representing solid, really spread apart representing gas, and kind of on top of each other, but not ordered representing liquid. And then last is just some practice with scientific notation. So go ahead and pause the video. Don't worry about this QR code. Pause the video and see if you can tell what this number is in scientific notation. All right, so the answer is D. If you got it right, you're good. Move on. If you didn't get it right, let's take a look. First scientific notation has to be number 1 through 9 before the decimal, and then times 10 to some n. So you can't have any number greater than 9 before the decimal, and you have to have times 10 to some n. N is how many times we have to move the decimal to get that number 1 through 9. If n is positive, the number is bigger than 1. If n is negative, the value of the number is less than 1 or smaller than 1. So let's look at this one. We need to move our decimal to be right here because we need one number to the left of the decimal 1 through 9. If I have the decimal here, that's 22, and that's bigger than 9, so I can't have the decimal there. So I'm going to count how many times do I have to move the decimal to get it there? 1, 2, 3 times. So the n is equal to 3. However, is this number bigger than 1 or less than 1? This number is smaller than 1, so it's going to be negative 3. So I'll rewrite this 2.250 times 10 to the negative 3. Hopefully that makes sense. If not, take a screenshot and text me, ask for some help. All right, what about this one? Go ahead and pause and try it. All right, answer to this one is B. If you got it right, cool, move on. If you didn't, hang in there with me. So we need to put our decimal here between the 6 and the 4 to give one number to the left of the decimal. Our decimal starts, even though it's not written, at the end here. So we need 1, 2, 3, 4, 5. So we have 10 to the 5. It needs to be positive or negative. Well, our answer options only have 1/10 to the 5, so we can just go with that. But why is this positive and not negative, which is maybe what you got wrong? It's because this is a larger number than 1. If you memorize the left and the right stuff, that's fine. If it's not working for you, then change. Big numbers, you would want a paycheck of it, positive number. Small number, don't bother with a paycheck of this much, smaller than 1, negative number, okay? And then let's do scientific notation back into regular notation. So go ahead and pause and try this one. Answer is A. If you didn't get it, hang out with me. If you got it, good work. So this is smaller than 1. Smaller number than 1. So we need to make this number smaller. We need to move our decimal, move decimal 2 times to make the number smaller. So if I'm moving my decimal to the right, that makes it to 3.5 turns into 35, and 350, that makes it bigger. So we got to move our decimal to the left 2 times, which means we're going to have a 0 here behind our decimal. So that gives us 0.035. All right, so that's all for that chapter 1 review. The rest of chapter 1 we actually are covering in class. And so if you have any questions, feel free to let me know.